And hello everyone, welcome back. Happy Friday. Today we're going to be finishing up with cycloalkanes and moving on to alkenes and seeing lots of cool stereochemistry that can happen because of these functional groups. So this is our last class that we're going to be using our cycloalkane, our cyclohexane. So hopefully you have that built today because we're starting with a clicker question. I'd like you to work with the person beside you. We'll add it here. Which of the following compounds can adopt a conformation where all of the chlorine atoms are in equatorial positions? So you can solve this on the paper. It's a whole lot easier if you build it with your model kit. So work with the person beside you for a minute and submit your answer. So hands together. Up to make a boat. So your boat is upside down. So take two opposite sides and bring both of those hands up. So kind of wiggle it a little bit and bring both of those hands. That's your boat. Now choose one hand and flip it down. There you go. Oh, yeah, there you go. And now if you set it down on your table, it'll sit on 3 prongs exactly. You have these 3 axials and 3 down axials. So there you go. That's your chair. Try doing the flip flop now. So the down, this is the down triangle, flip it up. Up triangle, flip down. There you go. So this is right here to the top side of the board. It was, yeah. So right there, you have a boat. So take 2 hands. And then so put your hands on opposite carbons. There you go. Which is opposite of this one. There you go. Yeah. So bring both of those hands up. That's a boat. Now bring one of those hands down, just one. There you go. And now see how it's 3 axial and 3 equatorial. This isn't clicked here. So that's, there you go. So click and push hard and then it'll have a nice angle. That's nothing. So bring both up and flip one side down. That's okay. Bring up and then keep this hand steady and just flip one side. And your pieces are also not clicked together. Yeah. So look here. So push and pull until they click. Oh. There you go. And 10 more seconds. And 3, 2, and 1. Okay, most people went for C, and I agree. Well done. We're going to look at some of these patterns with the document camera, and this will be our last cyclohexane. I have built option A, where I don't have all of these in equatorial positions. If we look at A, if I shoved my cyclohexane down and looked at all 3 chlorines, carbon 1, 2, and 4, as in A, pointing towards me, pointing up, then if I put this in a or in a chair conformation, so I'm going to bring it to a boat and flip one side down, I have axial, axial, equatorial. So those are not all equatorial. If I take the up triangle, flip it down, the down triangle, flip it up because I want to check my second conformation, I now have these 2 in equatorial positions. But this one is in an axial position. So I can't get all of them in equatorial positions based on A. Another way to notice this is if you look at adjacent carbons, ones that are directly next to each other. If one is in an up position, an axial, the next up position is going to be an equatorial. Axial up, equatorial up, axial up, equatorial up. It's a pattern. So if you have two substituents pointing towards you, one is going to be an equatorial, one is going to be an axial. If you do the chair flip-flop, the other one's going to be an axial, the other one's going to be an equatorial. If they're both pointing towards you, they can't both be in equatorial positions. But C, it's every second carbon. So in one chair conformation, I'm going to go ahead and make C. Hopefully you have that in front of you as well. Here, I can make this one in up equatorial positions for all of the carbons. If I did a flip-flop, I could put all three chlorines in axial positions, which is not what I want to do. But if I do my flip-flop, I can certainly change them to equatorial positions. So that's a handy pattern to notice. If they're coming towards you, adjacent carbons, those substituents are axial and equatorial, not the same. Okay, now we have a nice little summary here. We have just finished looking at different conformations of cycloalkanes. We can do our flip-flop to chair 1 and our flip-flop to chair 2. But we haven't broken any bonds. We haven't made any new bonds. That's simply a conformation change. These are still the same molecule. We didn't break any bonds. Same with when we were looking down the Newman projections. We're looking to see what substituents are close or farther apart, but we're not breaking any bond. So those are the same molecule, just in different conformations. But then we have our isomers. This is when we have the same molecular formula, but something's different about them. If they're constitutional isomers, that means the connectivity is different. For example, we could have the methyl groups off of carbon 1 and 3, or carbon 1 and 4. Different connectivity means constitutional isomers. If we take one of those molecules, one of the constitutional isomers, those two methyl groups could both be pointing towards us in a cis arrangement on the same side as that plane of carbons, or they could be opposite. They could be in a trans position. This is a type of stereoisomer. It's not constitutional because it's still the same connectivity. The methyl groups are still coming off of carbon 1 and 4, but now it's a stereoisomer, a different arrangement in three-dimensional space. So I hope this slide is helpful differentiating between these different terms. All of the examples we've looked at so far in 5.3 have to do with alkanes, cyclic or acyclic, but now we're going to move from alkanes to alkenes. Alkanes, you'll remember, had the formula of a ratio of carbons to hydrogens, where we have double the number of hydrogens plus 2 if it is an alkane. If we see that ratio, we know the molecule is saturated with hydrogens. It has as many as possible. And if it's an alkane, that means we don't have any double bonds. Of course, if it's a cycloalkane, that we had to remove 2 hydrogens to get there. Alkenes, as you know already, have one or more carbon-carbon double bond. In order to do that, we had to remove 2 hydrogens if we're going from an alkane to an alkene. So in this saturated alkane down below, I'm going to draw in all of my hydrogens, and I hope you follow along as well. This molecule, this pentane, has a ratio of 5 to 12. So double the number of hydrogens, 5 times 2 is 10, plus 2, 1 hydrogen for each end, which gives us 12. That is saturated. It has as many as possible. If we want to turn this into an alkene, we're going to have to take 2 hydrogens. I'm going to take this one and this one, Those hydrogens are going to go away. Those extra electrons can be used to form a double bond. I'm just going to turn this off for a second, and we're going to switch microphones. I was warned that one of the microphones wasn't working today, so we're back to our handheld now. Okay, so when we go from an alkane to an alkene, we had to remove 2 hydrogens to make that happen. Each of the carbons in the circled double bond is attached to 2 different substituents, as opposed to over here, each one was attached to 3. To do that, we had to remove 2 hydrogens. This alkene, this one double bond, we can now say this molecule has 1 unit of unsaturation. If we take away 2 hydrogens, then that counts as 1 unit. We're going to be working with these hydrogens in pairs because we need to remove 2 of them to get a double bond. Now, we just finished talking about cycloalkanes. So I'm going to go back to my C5H12. Imagine we put those 2 hydrogens back in. If I take 1 hydrogen from the end and another hydrogen from the end, as we did when we had our cycloalkane, we took those pieces. It's going to be tricky. We take 1 hydrogen from one end, 1 hydrogen from the other, and we use those pieces to form this into a cyclic structure. We had to get rid of 2 hydrogens to do that. So if I take away 2 hydrogens, I can now join up my cycloalkane. That also counts as a unit of unsaturation. For cycloalkanes, or for a molecule that has 1 double bond, an alkene, each of those has 1 unit of unsaturation. They've lost 2 hydrogens. If we see the ratio of 1 carbon to 2 hydrogens, or CnH2n, we know it has 1 unit of unsaturation. Maybe it's a ring, maybe it's a double bond. We'll need some more clues, but we know it has 1. Well, if I wanted to take away 2 more hydrogens, maybe I can take away these 2 from my cycloalkane. If I take those 2 away, I could have a cycloalkene. This cycloalkene has now 2 units of unsaturation. I've taken away 4 hydrogens to make that happen. Or I could take away these 2 hydrogens and form another double bond. Or I could even take away the 2 hydrogens at the double bond already. And we'll jump to another color here. If we take away 2 more hydrogens, 1 from each of those carbons, we end up with a triple bond. So we could have a molecule that has a triple bond, and that counts as 2 units of unsaturation. 2 to turn single to double, 2 to turn that double to single. An alkyne is going to have the ratio double the number of hydrogens minus 2. So based on the molecular formula, we can often predict, well, we definitely can predict the number of units of unsaturation. And then we can say, well, maybe it has a triple bond if it has 2 units of unsaturation. Or maybe it's a double bond and a double bond. Or maybe a double bond and a ring. We can have multiple combinations of unsaturation. Unsaturation meaning we don't have it saturated with hydrogens. We don't have the maximum number of hydrogens compared to the number of carbons. Okay, so question for you. How many units of unsaturation do each of these compounds have? The one on the left and the one on the right. Work with the person beside you and count the units of unsaturation. And 10 more seconds. And 3, 2, and 1. Okay, looks like we're split between C, D, and E. I'm going to actually double check my notes because the most popular answer is not the correct answer. The correct answer is D. So let's see how we can do that. There are 2 ways to calculate this or to determine this. First is simply to circle all the units of unsaturation. Circling the double bonds is nice and easy. 1, 2, 3, 4, 5. But then we have 2 rings. 6, 7. So that's how we get 7. Yes. My kids would be so happy right now. Okay. So it does have 7 units of unsaturation. We could circle them. That's probably the easiest way to do this. The other way I also want to show you, just in case you don't have the structure, we can write out the ratio of carbon to hydrogen. So the molecular formula for the molecule on the left is C10H8 once we draw in those implied hydrogens. If this was an alkane, if this was fully saturated with the maximum number of hydrogens, then it would follow the formula twice the number of hydrogens plus 2, which tells me that it would be 22. So if I want to calculate the units of unsaturation, 22 is the maximum possible. 8 is what I have, and they come in pairs, which tells me I have 7 units of unsaturation. So it also works that way. For the molecule on the right, we can see we can circle those double bonds. The oxygen doesn't really change the ratio. We could have had a hydrogen there or an oxygen, so we still are looking at the ratio of carbons to hydrogens. Okay, so units of unsaturation, we can figure out from the molecular formula and from the structure, and it gives us an idea of if we have perhaps double bonds or triple bonds or cycloalkanes or alkenes. We have ring structures. Okay, so we're now moving from alkanes to alkenes. If we have an alkene, that means we have a double bond. This is a reminder from a previous topic. We know that double bonds are made up of 2 components. They have the sigma bond, that direct head-on-head overlap of one orbital from one atom and another orbital from another atom. But in addition to that sigma bond, we also have the pi bond. And that's that sideways overlap of those p orbitals that are in a side-by-side arrangement. The one phase overlaps above the plane, the other phase overlaps below the plane. And these pi bonds cannot rotate. If my elbow to my hand is a p orbital, the other elbow to hand is a p orbital. If I try to rotate one of my hands, the phase overlap of the p orbitals is going to break. If we try to rotate a pi bond, it breaks. Sigma bonds we can rotate as much as we want. That's how we get cool conformations. But pi bonds don't rotate. And so this leads to another type of stereoisomerism because these double bonds, because of the pi bond, cannot rotate. This restricted motion leads to another type of isomerism. This is a type of stereoisomerism. We know isomers have the same molecular formula, but they're different somehow. Constitutional isomers are different because of their connectivity. Stereoisomers have the same connectivity. It's the same order of connection, but a different arrangement in three-dimensional space. Around a double bond, the type of stereoisomer that we're looking at is geometric isomer. The arrangement in three-dimensional space, even if we have the same connectivity. These isomers are also known as cis-trans isomers. We have them because we can't simply rotate the carbon-carbon double bonds. Well, we need to know when cis-trans isomerism is possible, and there are two rules to look at. The first is that we need to see that each of the carbon atoms in the double bond has two different substituents. So carbon 1 needs to have two different substituents. Here we can see it's a methyl group and a hydrogen. Those are different, so that's good. And then carbon 2 needs to have two different substituents. This one has a hydrogen and an ethyl group. We need to compare that each carbon has two unique substituents. In the molecule on the left, the interesting groups that aren't just hydrogen or the continuation of the carbon chain are on the same side of this double bond, which tells us it's a cis orientation on the same side. Now that's going to be different than if we take the substituents of the group on the right and put those in a different position. Now the two interesting groups, or the continuation of the carbon chain, are on opposite sides of this double bond, which gives us a trans isomer. So now it's time to pull out your model kit again. We're done with the cycloalkane for now. It's time to pull out your double bond. So I'd like you to go ahead and find two of these gray pieces. Notice that they're labeled sp2 hybridized. So we need two of those. And then you need to find this double bond piece. We're going to put it together and make an alkene. Now you can build the rest of the molecule using methyl and ethyl. I'm going to keep it simple today and just use different colored balls. So for my hydrogens, I'm going to leave those blank. For here, my methyl, I'm going to use blue, and ethyl, I'm going to use red. So go ahead and build the molecule on the left. And while you're at it, grab another double bond, that alkene, and build the molecule on the right, where the methyl group is pointing down off of carbon 1, and the ethyl group is pointing up off of carbon 2. When we try to rotate this double bond, you're going to see that we can't do that. We can only rotate it a little bit. Now that's in contrast to if we had an alkane here, and we can rotate that to our heart's content. Because these pi bonds in the double bond can't rotate, whether the red group is pointing down compared to the blue or up compared to the blue, it actually makes a different molecule. We can tell they're different molecules because we build the one on the left, we build the one on the right, and we try to overlay them. We can't overlay everything perfectly. I can overlay the carbon atoms and the blue methyl groups, but now the red atoms don't overlay properly. So if I try to overlay the red atoms, now the blue atoms don't overlay. So that tells me I have two different molecules. These are stereoisomers. They have the same connectivity, blue, gray, gray, red. Blue, gray, gray, red. Same connectivity, but different orientation in three-dimensional space. These two molecules are isomers, but the molecules below now on the screen are not isomers. On the left, we're going to go ahead and build that molecule. So use the same colored balls for the two methyl groups and a different colored ball for the chlorine. So here I've built the molecule on the left. I have a methyl group up and a methyl group down off of carbon 1 and a chlorine down off of carbon 2. And the same story for the molecule on the right with my chlorine pointing up. Now, rule number 1 on the screen is that cis-trans isomerism is only possible if each carbon has two different substituents. The carbon on the left has two blue balls or two methyl groups. Those are the same. Even though carbon on the right, carbon 2, has different substituents, red and gray, the one on the left has the same. So we're going to find that these molecules, even though they look different for the moment, aren't actually stereoisomers. Even though we've moved the chlorine to a different position, go ahead and pick up the molecule, see if you can overlay it to the first one to see if they're the same. I can overlay both blues, both carbons, both reds, and both hydrogens. These molecules are exactly the same. If we have one carbon atom in the alkene, or in the double bond, and it has two of the same substituents, we're not going to have cis-trans isomerism. Is the red cis to the blue, or is it trans to the blue? Well, it's cis and trans, so cis-trans doesn't even apply. These are the same molecules. But of course, if we take that off and we go back to our molecules at the top, we can see, oh, I took off the wrong one. We can see these do not overlay. So when we're trying to figure out cis or trans, we lay this down along the double bond. If they're on the same side, they're cis. If they're on opposite sides of that double bond, they are trans. Now, rule number 1, most important, look for two different substituents on each carbon atom. There is a second rule to consider, and this is only if cis and trans is hypothetically possible. For example, if this double bond was in a cyclohexane structure, these two substituents of that double bond have to be in that cis-looking position. I'm going to try to build that and try to build the trans, and we're going to see what happens. You can build along with me. So now I have my double bond in a cyclostructure, a cyclic structure, so it's a cyclohexene now. It looks like it's in a cis arrangement because the substituents off of the carbon-carbon bond are both on the same side, so they look like cis. But if we try to build the trans, if we try to rotate it, or even undo it and try to rotate it, we tried to build it as in this weird trans position. Look what happens to the double bond. I can't even put it together here. There we go. I'm breaking my model kit. Does that look like a molecule with good overlap of those orbitals? This pi is definitely not happening. That pi overlap is terrible. So that trans bond can't form. It's only going to form in this type of arrangement, which we don't even label as cis. It's the only option. So it's simply a cycloalkene. Cis-trans is not possible. So we're going to have a really big ring structure, something bigger than 7-ish, 6, 7, but more than 6, 7 or more, or 8 or more, to be able to have it big enough to also have it in that trans arrangement. Okay, I have successfully made a carbon-carbon double bond, so an alkene, in a cyclic structure. It's so big you can't even see it here. But you can see that the trans arrangement is actually in a trans arrangement, but now I have quite a large cyclic structure to be able to make that happen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and that's pretty happy. So cis-trans would be possible in larger structures. Once we know how many carbon-carbon double bonds in a compound could have cis-trans isomerism, we can calculate the number of possible stereoisomers for that connectivity of atoms by 2 to the power n. 2 times for the first bond plus 2 time options for the second double bond, and so on. So now we're going to we're going to draw out some cis-trans possibilities for this interesting molecule here. Here we are told we want to draw the 4 stereoisomers for this connectivity of atoms. So we're going to break this down a little bit to figure out what molecule we're talking about, and then we're going to draw all the different options. The first thing I want to notice is that I see 3 double bonds in this structure. I want to see which of these double bonds could have cis-trans isomerism. So I'm going to start with the first double bond here. It looks like CH-CH, but of course hydrogen is not involved in a double bond. We write out the order of the elements this way, but we know that hydrogen's not in the double bond. So this is actually a double bond between the carbon and the carbon. The carbon on the left is attached to the hydrogen and the methyl group, CH3. The carbon on the right is attached to the hydrogen and the carbon that goes to the rest of the molecule. So we want to look, the carbon on the left, I'm going to call this carbon 1 and carbon 2. Carbon 1, its 2 substituents are hydrogen and methyl. Those are different, okay? Carbon 2, hydrogen, and the whole rest of the molecule. Those are different as well. So this bond can have cis-trans isomerism. There's no ring that I have to worry about as well. Now I'm going to go to the next double bond. And I know that this one is a double bond between the carbon and the carbon, not the hydrogen. The carbon on the left is attached to hydrogen and the rest of the molecule. The carbon on the right is attached to hydrogen and the rest of the molecule. Hydrogen compared to the rest of the molecule and hydrogen compared to something else. Each carbon has 2 different substituents. Thumbs up, this one can have cis-trans isomerism. Well, then we go to the third carbon-carbon double bond, and it's a double bond between those 2 carbon atoms with the purple dots. The one on the left has 1 substituent of hydrogen and another substituent of that carbon connected to the whole other part of the molecule. Those are different, that's good. The carbon on the right is connected to a hydrogen and a hydrogen. Those 2 hydrogens are not different. Therefore, the second carbon in this double bond doesn't have 2 different substituents. This double bond cannot have cis-trans isomerism. But the first 2 can. So the first 2 bonds, perhaps they could be in a cis, and then the second one in a trans arrangement. Or perhaps it's cis and cis, or trans and cis. What's the final option? Trans and trans. That's how we get 4 stereoisomers, 2 bonds that could have stereoisomerism. 2 options for each one gives us 4 options. So we're going to take a minute or 2 to draw out the first option laboriously, and then we're going to draw the remaining 3 much faster. So I'm going to start with a cis and trans arrangement. Now, my strategy when I have to do this type of thing is to choose the first double bond and build my structure around that. So I'm going to start with my double bond here. I'm going to draw the carbon on the left with its hydrogen and methyl group. And then my carbon on the right, it does matter where I place these groups because I want to start with my circled geometry in cis-trans. So I want this one to be a cis. So I'm going to put the interesting groups or the continuation of the carbon on the same side of the double bond. So this is going to go down to a carbon, which means the up position to a hydrogen. Then I'm going to continue along with my fourth carbon in. And my fourth carbon in, I see I'm getting to that blue check mark double bond. The carbon on the left with the blue arrow, we can see it also has a hydrogen. And then a carbon-carbon double bond, so my next C. I'm in my blue check mark here. The carbon on the right is connected to a hydrogen and the rest of the molecule. I'm aiming to make this one a trans arrangement. So I'm going to put, since the carbon on the left has an up interesting substituent, the carbon on the right is going to have a down interesting substituent. So the rest of the molecule is going to continue this way. And then I'm now to my last carbon-carbon double bond that doesn't have cis-trans isomerism. We can double check by counting the number of carbon atoms to make sure we got everything in. And we have drawn the cis-trans stereoisomer. We've drawn one of the 4 options. I'm going to show you how we can draw this a little bit easier. I'm going to draw the cis-trans again. I'm going to start with my double bond, the methyl down to the right, another double bond, and another double bond. So this is also the cis-trans molecule, but now I'm just drawing it in my line diagram. Much faster, much easier. And we're done our cis-trans one. Let's go ahead now and do our cis-cis option. So I'm going to draw that one over here. I'm going to start with a cis arrangement. Then my next double bond also needs to be in a cis arrangement. So I have to put the interesting groups on the same side. And then my third double bond that doesn't have cis or trans. So that is my cis-cis arrangement. And now I'm going to draw my trans-cis arrangement. So I'm going to start with a trans option, and then make a cis arrangement, and then finish off with my double bond. And my last option is going to be my trans and trans. So starting off on opposite sides, the next double bond, also on opposite sides, and then finish off with the final double bond. Whew. So it's a little bit of work, but we can totally do it. This is how we get 4 stereoisomers, 2 double bonds in the molecule that can have cis-trans isomerism. 2 to the power 2 gives us 4, and we have drawn 4 unique molecules. We can't rotate and do different conformations to get any of these. We have to build it differently. We have to break bonds and form new bonds to form this structure. Okay, I'm going to leave that up on one slide in case you're still writing there, because we are going to chat a little bit about why we're talking so much about alkenes. You probably already know this, but alkenes are very important. Alkenes, these double bonds tend to be quite reactive, and you could do all sorts of different reactions, organic reactions, to produce all sorts of different types of molecules because you started with that carbon-carbon double bond. You could add water, H2O, which means you can add hydrogen to one of those carbons, OH to the other. You could do this hydration reaction and make alcohols. Maybe you want to add some hydrogen. You can saturate those carbons with hydrogen and make alkanes. Butter is typically saturated on the whole. Oil is typically unsaturated, and they have different properties. If you want to increase the melting point, you can saturate it. If you want to increase the shelf life of food, you can react those double bonds because they're reactive. And so a lot of food processing likes to take out some of those double bonds to keep the food lasting longer. We can make things like epoxides and glues. We can make halides like chlorofluorocarbons that are important in Teflon and plastics. We can make all sorts of very important molecules. No, you don't need to memorize this, but realize that we can do all sorts of cool stuff with double bonds. So we need to know if they're cis or trans, what the options are, and lots of cool chemistry happens with alkenes. In our bodies, alkenes are also very important. As you probably know, you need to make sure you're eating your vitamins with a healthy diet. And carotene, or vitamin A, is also very important. Carotene is a precursor to vitamin A. Helps with vision, helps with growth. And vision is what we're going to be talking about here. This beta carotene molecule kind of large. Your body can break it down into two pieces, and one of those pieces is retinal. When you see that Al, you'll see it has an aldehyde. That's how we know what functional group it has. Other interesting functional groups are that it has a lot of double bonds, and you'll see that these double bonds are in trans positions. They're on opposite sides where that carbon chain continues. And we have a cycloalkene over on the left-hand side. Now, this molecule is in your eyeball, and it is essential for vision. You have a protein in your body that can take this trans version where all those double bonds that could be cis or trans are in trans positions. This enzyme is able to do an isomerization reaction, break the pi bond between the indicated carbons here. The pi bond breaks, the sigma bond stays, and we know sigma bonds can rotate. The pi bond is broken, the molecule can rotate, and then it reforms in this cis position. So the other bonds stayed the way they were, but this one changed. This was a reaction. It's not a conformation. We actually had to do a real process where we broke the pi bond, reformed it to form this cis isomer. Well, once we have the cis isomer, it's just the right shape to be able to combine with your opsin protein. And so there's a reaction that occurs that binds what was retinal onto your opsin protein. And now it's ready for your eyeballs, your retina, to detect light. And if light of just the right wavelength comes in, a photon, it has just the right energy to break that pi bond and cause another isomerization. So a new isomer is formed. It's a photoisomerization reaction because it's done by a photon, by light. And that cis bond reforms as a trans bond. Now look at the shape of the cis retinal compared to the trans retinal. Do you see how this one is kind of like this type of position and the cis is kind of like curvy like this? That change from the cis to the trans causes a change in the shape of the molecule, which changes the shape of the protein, which causes this cascading reaction to send a signal to your brain, which says, ooh, there's light. And this is how your vision works. Well, once it's back in trans position, it's no more use. It's no more good. How do you say that? It doesn't detect light anymore. It's useless at this moment. So a reaction happens, it's detached from the opsin protein. Now it's back to trans, and it has to be reconverted back to the cis to join back to that protein. And this cycle continues over and over. And it's pretty cool. I have one more question for you. Look at this retinal molecule. How many cis-trans stereoisomers are possible based on the connectivity of this molecule? We know we have to have just the right combination of cis and trans for it to be retinal that works in your eyeball. But hypothetically, based on the connectivity, how many stereoisomers are possible for this arrangement of carbon atoms? Chat with the person beside you. If you do that really fast, feel free to chat about what IR features you look for in a spectra of this molecule as well. And 10 more seconds. And 3, 2, and 1. Okay, most going for, ooh. There we go. You're making me second guess myself today. Okay, so 2 to the power 4, which of these could be cis or trans? Those are the ones that could be cis or trans. The one in the cycloalkene can't be different, and an aldehyde can't be different either. So 2 options times 2 options times 2 options is what we have. Okay, well done. Bring your model kits next class. We're going to be working with our alkenes again. I will see you next week. Thank you so much.